In this paper, we introduce a framework for instantaneous perception of moving objects in 3D. This work is resulted from collaboration between Rutgers University and NEC Labs America. Moving object detection and their motion estimation are critical for autonomous driving because surrounding dynamic objects are safety-critical factors that may change the decision-making in autonomous driving. Prior motion detection works mostly handled generic large motion, which are prevalent in driving scenes. In this paper, we argue that large motions can be reliably perceived by modern 3D object detection and tracking system. Instead, we focus on the small motion regime wherein the signal-to-noise ratio is lower. An important application of small motion perception is to enable instantaneous perception of object motion as soon as objects start moving. This allows to understand their driving intention instantly and reduces the latency for the autonomy to respond accordingly. This video demonstrates examples for small motion perception in an intersection where the two vehicles on the right side intend to pass the ego car and make right turn. In this work, we propose a framework, named as SMORE, for small motion perception, which may be integrated into a practical 3D object tracking system. Specifically, 3D object and tracking algorithm reliably identify objects with large motion, but it faces challenges in distinguish small motion and static objects due to imperfect object localization. Our SMORE operates in this regime to further detect slowly moving objects and estimate their motion. A unique challenge for small motion perception lies in the so-called swimming effect in LiDAR point clouds. As shown in prior work, LiDAR captures different sets of sparse points when there is relative motion between LiDAR and the scene being captured. This means no correspondences exist for the two LiDAR scans, and points may appear to be swimming even if they are static. This swimming effect intertwines with the point displacements caused by real object motion, posing ambiguity especially under small motion. This illustrates the pipeline of our proposed SMORE framework, with a view to tackling the swimming effect by object shape completion. Our framework takes 5 sequential LiDAR frames as input and extract objects that may be either static or with small motion. Our goal is to detect and estimate motion if the object moves at least 0.05 ms in a 0.5's latency, else the objects are deemed as static. For each object, we first perform voxelization to convert points into binary grid. It is then passed to a CNN-based encoder-decoder network for shape completion prediction in the form of occupancy grid. This step effectively densifies the object points, which mitigates the adverse impact from swimming effect. The ground truth of shape completion is collected by aggregating nearby LiDAR frames. The densified occupancy grid is then passed to another encoder-decoder network for motion detection and motion flow estimation, which are supervised by their ground truth. We performance evaluation on a small motion-specific dataset curated from Waymo Open Dataset, with F1 score as the detection metric and EPE plus angular error for the motion flow estimation. Our method outperforms point correspondences-based methods like ICP and scene flow estimation approach as they inherently suffer from the ambiguity posed by swimming effect and occlusions. In addition, deriving motion from 3D detection and tracking methods also faces challenge in small motion regime due to its imperfect object localization. We illustrate here that SMORE is capable of achieving accurate motion flow by showing good alignment between points warped from frame T1 with motion flow to frame T and the points observed in frame T. Finally, we demonstrate SMORE on an example where the ego car navigates through an intersection. While the large motions dominate the scene, we highlight the capability of SMORE in perceiving the small motion of the white car that indicates its intention to take a red light right turn.